Alright, so now we continue with methods of partial fractions. So now when we go to method number 2, it's going to be those that have a denominator with a quadratic factor that is not factorable. So now we've been dealing before with those that have linear factors, but now let's look at what those that are quadratic factors are. So a quadratic factor or an irreducible factor is a quadratic factor actually. Now we're looking at those that are irreducible. So an irreducible factor is a quadratic factor which does not itself factor into two linear polynomials. If plugging in the quadratic into the quadratic formula generates answers with square roots or complex values, then the quadratic is irreducible. So now what do these look like? We shall see them in our examples. So example number 1, we're being told to express 3x squared minus 2x plus 5 over x minus 1 times x squared plus 5 as a partial fraction. So this again is a proper fraction, as you can see. And now there is actually something unique here. As you can see, when you look at the denominators, we have this value x squared plus 5. As you can see, there is no further way I can actually simplify this. There is no more factorization I can do to make this simpler. So this just stays as x squared plus 5. So you can actually see that this value here is irreducible, and it's also not a linear factor. Remember that a linear factor has x but to the power 1. Now this has x to the power, it has an x squared plus 5. So this is actually a quadratic factor, but this one is actually irreducible. So these are the kind of numbers that we are looking at. So what you can see is x squared plus 5 does not factor into linear polynomials. So that's actually an irreducible quadratic factor. So we're going to let this value here be equal to a over x minus 1. But now where there is a quadratic factor, so remember that every single time we were placing unknown constants as numerators of the simple fractions. As you can see, now we're going to have the numerator of this linear factor here. This linear factor here is a, so it's going to be a over x minus 1. But now the difference here is wherever there is an irreducible factor or that quadratic factor x squared plus 5, we're going to also insert unknown constants, but the unknown constants are going to be in the form bx plus c. So wherever there is, you're going to multiply to the very first constant, you're going to multiply an x, and then you're going to add the next constant. So it will be in the form of bx plus c. So this is unique to those that have a quadratic factor. So now when we find the LCM there, we can actually see that we'll have, so this is how we have the LCM. So the LCM is going to be x minus 1 into x squared plus 5. So when you get this, divide by x minus 1, we have x squared plus 5 times a. And then when we get this LCM here, divide by x squared plus 5, we remain with x minus 1. So we have x minus 1 times bx plus c. So therefore, as you can see, when we cancel out these denominators, we remain with 3x squared minus 2x plus 5 being equal to that, the numerator value right there. So as you can see, now in this case, if we want to find the value of if we want to find some unknowns, as you can see, the quickest way is, if I want to find a, for example, all I have to do is to just make x be equal to 1. Because if I make x be equal to 1, this will be 1 minus 1, which is 0, and then 0 times these 2, and then I'll be able to find the value of a. So in this case, that's what I'm going to do. So every single time when it comes to quadratic factors, I'll be finding one of the values, and then I'll use that knowledge to find the others, as we shall see. So if x is equal to 1, we can actually see that this is what we end up having. So we're going to eliminate this side that has the b and c, and we'll be left with this. So we'll be left with 6 being equal to 6a when we eliminate the rest. So as you can see, a shall be equal to 1. So now that we know that a is equal to 1, you can actually see that since we have bx plus c on the other side, we may not be able to directly solve as usual as we've done before, but there is a simpler way of doing it this time. What happens is we're going to get this equation that we have here, 3x squared minus 2x plus 5 being equal to that. But now the difference is we know what the value of a is. We know that a is equal to 1. So if a is equal to 1, that means we're just left with x squared plus 5 right here. And then right here, we're going to multiply this times that, and then we'll have bx squared minus bx plus cx minus c. So next we're going to arrange everything. we're going to arrange everything. All values that have the same powers, we're going to bring them together. So those values that have x squared, we're going to bring together. Those values that have x will combine together, and then those values that don't have any power of x, so we're going to combine those together, and then this is what we end up having. So now when we pull out x squared from this, we are left with 1 plus bx squared. Then we can arrange this as cx minus bx. Of course, when we pull out x, we'll have c minus b. Then right here, we're left with 5 minus c. So now the next step we're going to do is we're going to equate corresponding coefficients on both sides. So we're going to compare this coefficient here to this coefficient right there. And then we're going to compare this coefficient here to this one, and then this coefficient here to that. So if we compare the coefficients, you can actually see that this 3 here is equal to 1 plus b. So when you do that, we can actually see that b shall be equal to 3 minus 1, which is 2. So b is equal to 2. So now that we know b, alright, so now we can also see that the easiest way of finding c is actually, we can actually ignore this, we can actually just go straight to this. So 5 minus c, we can actually see is equal to 5. So 5 minus c is equal to 5, of which c shall be equal to 0. So now we know what a is, we know what b is, and we know what c is. So therefore, our equation in partial fraction shall be equal to this. So 1 over x minus 1. But remember that our b value is 2. So 2x, that's what we have here, plus 0, because c is 0. And then we'll be having 1 over x minus 1 plus 2x over x squared plus 5. And that is how we express these kinds of numbers with quadratic factors into partial fractions. Alright, so let's move on to another question. So I'm being told to express 11x over 2x minus 3 over times 2x squared plus 1 as a partial fraction. So now clearly you can already see that we have a linear factor right here. So 2x minus 3 is linear, but also we see we have this 2x squared plus 1. Now you can see that there is no way you can factorize this or simplify this any further. So we're left with 2x squared plus 1. So this is an irreducible factor. So we're going to treat it the way we treat other quadratic factors. So now we have 2x squared plus 1, which does not factor into linear polynomials. So therefore we're going to let 11x over 2x minus 3 times 2x squared plus 1 be equal to a over 2x minus 3. But remember, where we have that quadratic factor 2x squared plus 1, we're going to have a bx plus c. So this is how it's going to look. So we're going to solve this. So now we can already see that the LCM shall be equal to that. So the LCM is 2x minus 3 times 2x squared plus 1. So when you get this value here combined, divide by 2x minus 3, we get 2x squared plus 1. When you multiply to a, and then this value here divide by that, we remain with 2x minus 3 times these values right there. So the next step is now we can eliminate the denominators, and we're left with 11x being equal to that. Now we can say the quickest thing we can do is we can already solve and find the value of a. And how are we going to find a? We can already see that all we have to do is equate this to, so if we make x be equal to 3 over 2, we can actually see that this 2 can cancel, and we'll be left with a 3. 3 minus 3 shall be equal to 0. So we shall have this part cancelled, and you can easily find the part with side a. So if we make x be equal to 3 over 2, this is what we end up having. So a can be found. So we'll have 33 over 2 being equal to 11 2 of a, of which a shall be equal to 3. So that's going to be a quick way of finding a. So now that we know a, we can actually simply solve this part right here, and then we shall just equate and compare the coefficients on both sides. Right, so this is what we have. So next we're going to, now that we know a is actually 3, then we're going to open brackets. So 3 into this is what we have. We have 6x squared plus 3. Then when we multiply this bracket to this bracket, we have 2bx squared minus 3bx plus 2cx minus 3c. So now we're going to combine different values that actually have the same powers of x. So now we have cx squared combining with this, then cx combining with this, and then that. So now next we're going to group all of them, and then we're going to simply compare the coefficients on both sides. So now we can actually see that this and this. So now if we equate corresponding coefficients on both sides, we can actually see that 6 plus 2b shall be equal to 0, because we don't have the coefficient that actually has the x squared is actually equal to 0. That's why it's not, doesn't appear right here. So we have that. So 2b shall be equal to negative 6, of which b shall be equal to negative 3. So now we know b. So how are we going to find c? So now we're going to find c from here. So you can actually see that 2c minus 3b is equal to 11, as you can already see, because this is x, that is x. So, but we know what b is. But we know that b is equal to negative 3. So now we have 11 being equal to 2c plus 9. So we have 11 minus 9 is 2. So we have 2c being equal to 2. And then c shall be equal to 1. So now that we know all the values, so therefore this is what we're going to have as our partial fractions. So these are going to be our partial fractions. And that is what they wanted. Alright, so moving on to question number 3, we're being told to express 1 over x power 4 plus 5x squared plus 6 as a partial fraction. Now I can already see that there is a possibility of reducing this a little bit, but that's what we're going to do next. So now if we're to consider x power 4 plus 5x squared plus 6, we can actually see that this can be expressed in quadratic form this way. So we have this is the same as x squared plus 5x squared plus 6. So we can actually let m be equal to x squared and then first solve that and simplify. So m squared plus 5m is plus 6. So this is what we have. So we're going to like solve that quadratic equation to actually simplify it. So we'll have m into m plus 2 plus 3 into m plus 2. What happens is right here, between these two we factorize out m, and between these two we factorize out 3. And as you can see, we'll be having the brackets m plus 3 and m plus 2 multiplying each other to form that. But remember what our m value represents. M is x squared. So we have x squared plus 3 into x squared plus 2. So now this is a unique example because as you can see, we have two irreducible factors, irreducible quadratic factors. We have x squared plus 3 and x squared plus 2. So what are we going to do? So now, therefore, this is what we have. So therefore now, this is the same as that. So we're going to let, so both x squared plus 3 and x squared plus 2 do not factor into linear polynomials. So we're going to let 1 over x squared plus 3 times x squared plus 2 be equal to, as you can see, since both are irreducible quadratic factors, we're going to have an ax plus b over this and a cx plus d over that. So that is because both of them are actually irreducible. So that's how we write them in partial fraction form. So now we're going to need to find a, b, c, d. So this is a unique example because we have very many unknown constants, but this is still doable. So actually, let's first find the LCM. So when you find the LCM, we can actually say the LCM is x squared plus 3 times x squared plus 2. When you get this value, divide by x squared plus 3, we get x squared plus 2 and multiply it up here. This divide by x squared plus 2, we have x squared plus 3, multiply it up there. So this is what we have. We cancel out the denominators and we're left with those values of the numerators. Alright, so this is going to be the first thing. Now we ask ourselves the question, is there a possibility of at least knowing one of the letters? As you can see, it's not that direct, it's not that directly possible. So what we're going to have to do is we're going to have to take it slow. So what we're going to do is we're going to just open brackets right here. So we're going to open brackets and just solve. So as you can see, when you multiply this and this, we have ax cubed plus 2ax plus 2bx squared plus 2b. And then when you open these brackets, we have cx cubed plus 3cx plus dx squared plus 3d. Then we're going to arrange them and we're going to collect terms that actually have the same powers together. So we have x cubed plus 3x cubed. We have bx squared plus dx squared. Then we have 2x plus 3cx and then 2b plus 3d. So we're going to put all those in brackets. So now that is what we have. So now the next step is going to be for us to compare the coefficients on both sides. So we're going to equate corresponding coefficients on both sides. As you can see, we'll have a plus c shall be equal to 0 because the coefficient of x cubed on the left hand side is 0. And then we also have b plus d being equal to 0. And then next we have 2a plus 3c shall also be equal to 0. And then lastly, we can actually see that 2b plus 3d is equal to 1. So that's what we have. So let's solve this. So from equation 1, we can actually see that we can make a the subject and a shall be equal to negative, b equal to negative c. So we're going to substitute for a in equation 3. because in equation 3 we have an a and a c, so we're going to equate substitute it there. So when you substitute for a there, we have 2 into negative c plus 3c being equal to 0. So we have negative 2c plus 3c being equal to 0. Then we shall end up having c as being equal to 0, and that is going to be the value of c. So if c is 0, it therefore means that a shall also be equal to 0, because a is equal to negative c, and negative 0 is 0. So from equation 2, we can also see that b shall be equal to negative d. So therefore, if we substitute for b in equation 4, we have 2 into negative d plus 3d being equal to 1. So d shall be equal to 1. And if d is equal to 1, it therefore means that b shall be equal to negative 1, because b is the negative, the other value with the negative of d. Alright, so now we know what a, b, c, and d are. Now we can substitute that, so therefore we have this. So we have 0x plus negative 1 over x squared plus 1 plus 0x plus 1 over x squared plus 2. So this is 0 and this is also 0. So we have negative 1 over x squared plus 3 plus 1 over x squared plus 2. So let's rearrange this. So we'll have this minus that. And that's going to be, that's how we express that as partial fractions. Alright, so let's move on to another one. So this is question number 4. So being told that 2x plus 1 over x cubed minus 1 as a partial fraction. So we're being told to express that as a partial fraction. So how do we solve this? So now if we consider x cubed minus 1, we can already see that that value is the same as, so this can also be the same as x cubed minus 1 cubed. And we know that any value that is a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So it can actually be expressed that way. So therefore x cubed minus 1 is equal to x minus 1 times x squared plus x plus 1. So now that is another way of expressing it. But also we can now see that we can now not express this any further. So we can no longer factorize this value here any further. So this is going to be left as it is. So x squared plus x plus 1 does not factor into linear polynomials. So therefore that is an irreducible quadratic factor. So we're going to let 2x plus 1 over x minus 1 into x squared plus x plus 1. So wherever there is this linear factor right here, we're going to have an a, and then where there is this irreducible quadratic factor, we shall have bx plus c over that. So this is what we end up having. The LCM is this. So this divided by x minus 1 is x squared plus x plus 1. And then this divided by that, we'll have x minus 1. Multiply it there, and that's what we have. So next we're going to cancel out the denominators, and we're left with that. So now this is an easy one. So we can actually eliminate b and c, and we can actually first find the value of a. So how do we do that? We can actually make x be equal to 1, because if we make x be equal to 1, 1 minus 1 is 0, 0 times this cancel, and we find the value of a. So we're going to let x be equal to 1, then this is what we shall end up having. So end up being left with 3 being equal to 3a, and a shall be equal to 1. So now that we know the value of a, next we need to find the value of b and c. So next we're going to go to our general equation, and we're going to substitute in the value of a. A is 1, so that's what we end up having. But also we can actually see that we can actually multiply these two brackets, and we have bx squared minus bx plus cx minus c. Then we can actually see this is what we have. So now let's collect terms that actually have the same powers of x. So this is what we have: x squared plus bx squared plus x plus cx minus bx plus 1 minus c. So now when you group them, this is what we end up having. Now we can actually now compare corresponding coefficients on both sides. So now first thing we can see is 1 plus b shall be equal to 0. So therefore b is equal to negative 1. Then we can also see that 1 minus c minus b shall be equal to 2. So these equate to this coefficient right there. So therefore, but we know what b is, so we have 1 minus c plus 1. So therefore we can actually see that c shall be equal to 0. So now that we know that, so therefore this is what we have: 1 over x minus 1 plus negative 1 x plus 0 over x squared plus x plus 1. And therefore finally we have 1 over x minus 1 minus x over x squared plus x plus 1, and that is the answer we're looking for. Alright, so question number 5, we're being told 13x plus 7 over x minus 4 times 3x squared plus 2x plus 3. So we're being told to express this as a partial fraction. So now let's consider this. So we can actually say that 3x squared plus 2x plus 3 does not factor into linear polynomials. So that one is clearly irreducible. So we can already let this be equal to a over, since this x minus 4 is linear, we just have it as a over x minus 4. Then since this is an irreducible quadratic factor, we have bx plus c over that value. So therefore the LCM shall be x minus 4 into 3x plus 2x plus 3. So when you get this, divide by x minus 4, we're left with this itself times a. And then this LCM divide by that, we're left with x minus 4 times that. Then we can actually see that the denominator values cancel, and then this is what we are left with. So now the next step is we need to first find the value of a. So how do we do that? We can actually set, if we let x be equal to 4, we can actually eliminate this and we can find the value of a. So if we let x be equal to 4, this is what we end up having. So we have 559 on the left hand side being equal to 59a. So therefore a shall be equal to 1. So now that we know the value of a, we can actually now consider this equation. We know what a is, so a is 1, we substitute in 1. Then we can actually multiply these brackets and we have bx squared minus 4bx plus cx minus 4c. So now we can combine values that have the same power of x together, we group those together, then this is what we end up having. So next we equate corresponding coefficients on both sides. So we can actually see from here 3 plus b shall be equal to 0 because the coefficient of x clearly on the left hand side is 0, the coefficient of x squared. So we can actually say that b is equal to negative 3, and since we know what b is, we can now go to this. So 2 minus 4b plus c shall be equal to 13. So we know what b is, so we substitute it in. So we're left with 13 being equal to 14 plus c, and c shall be equal to negative 1. So therefore we have 1 over x minus 1 minus 3x plus 1 over 3x squared plus 2x plus 3. And this is how we express it in partial fractions. Alright, so now this is now the other question, but now this one encourages us to later on, after we express as a partial fraction, we're being told to integrate that. So we've been given 3x plus 1 over x minus 1 times x squared plus 1. We're being told to express that as a partial fraction and hence evaluate it or find the integral. So first step first, we're going to first express that as partial fractions. So now we can already see that x squared plus 1 does not factor into linear polynomials. So therefore we're going to let 3x plus 1 over x minus 1 into x squared plus 1 be equal to a over x minus 1. Because this is linear, we just put it that way. But then because this is irreducible, we have bx plus c over x squared plus 1. So now next we find the LCM, and when we find the LCM, these are the terms which have at the numerator, and then we can actually see that the denominator value is cancelled, and this is what we're left with. So next we're going to first find the value of a, but how to do that? We're going to let x be equal to 1, because when we let x be 1, this shall become 0, and then we shall eliminate b and c, and we shall easily first find the value of a. So if x is 1, this is what we end up having. 4 is equal to 2a, and a shall be equal to 2. Alright, so now that we know that, we get this equation right here, and then we're going to work on it and just compare coefficients. So we know that a is 2, so we're going to substitute that in there. So 2 into this, we'll have 2x squared plus 2. Then we multiply these two brackets, we have bx squared minus bx plus cx minus c. So now we're going to group the values that have the same powers of x. And then this is what the group will actually look like. So now that we have that, we're going to compare or equate corresponding coefficients on both sides. So we can actually see that 2 plus b shall be equal to 0. So we have b being equal to negative 2. And then c minus b shall be equal to 3. And then we know that b is equal to negative 2. So c shall be equal to 1. So therefore, the partial fractions are this. So this is what we end up having. 2 over x minus 1 plus minus 2x plus 1 over x squared plus 1. So that's what we have now. So now integrating the partial fractions. So we're going to now integrate them. Now we first group them this way. So we're going to integrate them that way. But we can actually see that this value here can actually be split into two different fractions again. So this can be split into negative 2x over x squared plus 1 plus 1 over x squared plus 1. But actually, as you can see, this negative will affect this plus, and this is what we end up having. So next, we're going to now work on integrating them. Now, we can actually see that to integrate this part here, we can actually just use U substitution, and then we'll have ln x minus 1. Then to integrate this part here, we also use U substitution, where we'll let u be equal to x squared plus 1, and then we will end up having ln x squared plus 1 for that. Now when we go to this one, we can actually say that this actually requires trigonometric substitution, that which has tan, so tan substitution. So when we do that, we'll have tan inverse of x plus c, and that's going to be our answer right there. But as you can see, we can actually simplify this even further. So this 2 can be brought here, and it can be made a power of ln, and then we can actually see that when we have this subtracting that, it's the same as ln x minus 1 squared over x squared plus 1 plus tan inverse of x plus c, and that is what they wanted. So question number 7, we're being told to show that the integral of x squared plus 6 over x squared plus 4 times x squared plus 1 shall equate to pi over 20. But now we've been given limits on that integral, the limits of 1 and 0. So how do we do that? We can already see that clearly this is a proper fraction, so it's okay for us to proceed. But then when we look inside, we can actually see that we have both x squared plus 4 and x squared plus 9 do not factor into linear polynomials. So we actually have two irreducible factors. So we're going to let x squared plus 6 over x squared plus 4 times x squared plus 9 be equal to that. So now that is what we end up having. So we now have unknown constants of a, b, c, and d, and that's what we're going to have to work out. So this is what we have. So we find the LCM on the right hand side, and this is what we have. So this divide by that, we are left with x squared plus 9. So we multiply it on the left. Then this divide by this, we are left with x squared plus 4 and multiply it on the right, and that's what we have. So next, we can actually see that the denominator values cancel. Then we have x squared plus 6 being equal to that. And now we can actually say there is no direct way of finding a, b, c. So what we're going to do is we're going to just solve this and just open brackets. So we have x squared plus 6 be equal to, so when we multiply this bracket and this, we have x cubed plus 9ax plus bx squared plus 9b. Then when we multiply these two brackets, we have cx cubed plus 4cx plus dx squared plus 4d. So now we're going to combine terms that actually have the same powers of x, and that's what we have. So now when you group them, this is what we end up having. So the next step is going to be for us to equate corresponding coefficients on both sides. So as you can see, we have a plus c shall be equal to 0, because the coefficient of x cubed on the left hand side definitely must be equal to 0, because we don't see the x cubed value. So next we can actually see that b plus d shall be equal to 1. Then we have 4a plus 9c being equal to 0, and then we can actually see that 9b plus 4d shall be equal to 6. So from equation 1, we can see that a, we can make a the subject and a shall be equal to negative c. Then we substitute that into equation 3, substitute for a in equation 3, then this is what we end up having. So we have negative 4c plus 9c being equal to 0, of which 9c minus 4c is 5c. So 5c is equal to 0, of which c shall be equal to 0. Now if we know c, we can actually therefore know what a is. So a shall also be equal to 0, because a negative 0 is 0. So from equation 2, we can actually see that b is equal to 1 minus d if we make b the subject. So when you substitute that into equation 4, for b in equation 4, we shall have 9 into 1 minus d plus 4d being equal to 6. So we have 9 minus 9d plus 4d is equal to 6. Then we have 9 minus 5d being equal to 6. 5d shall be equal to 3, because 9 minus 6 is positive 3. So therefore D shall be equal to 3 over 5. So therefore if D is 3 over 5, it means B shall be equal to 2 over 5. So when you substitute those in to set our partial fractions, this is what we have. So we're left with 2 over 5 over x squared plus 4 plus 3 over 5 over x squared plus 9. So when we correct those, you can actually see that the denominator values combine, and this is what we end up having. So now we know that. So now the next step is to integrate the partial fractions. So you can actually say the integral of this shall be equal to the integral of these partial fractions. Now clearly we can already see that we can actually pull out a 1 over 5 from both, and this is what we're left with. Alright, so now both are solved by trigonometric substitution. As you can see, there is no other way. Now in this question, U substitution cannot work, and there is no other method that will work. It's clearly trigonometric substitution. So when we use trigonometric substitution, this is what we end up having. So for this side here, we have 2 tan inverse over half x, and then this we have 3 into a third tan inverse of a third x. But remember, this 1 over 5 is outside, and then we have the limits 1 and 0. So now those are very important for you to remember. So next we're going to insert the limits, and then we're going to have those values that have the limit of 1, and then we have those that have 0. Then as you can already see, what we did first is 2 times a half is 1. So that's why we don't have this a half and the 2. And then right here, a third times 3 is also equal to 1. So that's why we no longer have that value right there. So next we can actually see that tan inverse, of course, a half times 0 is 0, and tan inverse of 0 is 0. So now that means this is 0 plus 0. So these are unnecessary, so we're only left with this side right here. And then 1 times a half is obvious a half, and 1 times a third is a third. So this is what we're left with right here. But remember that what we're trying to prove is, remember our proof, so this is not the end of it. So now we have to find a way of converting this into values that actually have pi in them. So how are we going to do this? We're going to use some knowledge of trigonometry. So what we're going to do is we're going to let A be equal to tan inverse of a half, and then we're going to let B be equal to tan inverse of a third. And then the next step is going to be, we can already see that tan A shall be equal to a half and tan B shall be equal to a third. Now we're going to remember something from our knowledge of trigonometry. You remember that tan A plus B is equal to tan A plus tan B over 1 minus tan A tan B. So now our desire is we want to find out what A plus B is equal to. And that is going to be what is going to help us in this proof right here, because this is going to be A plus B. So we need to find the unknown A plus B. But before we do that, let's first solve for this side here. So we're going to substitute in the values of tan A and tan B, and that's what we end up having. So this is what we have. And then we have 5 over 6 over 1 minus 1 over 6. Then we have 5 over 6 divided by 5 over 6, which is 1. So now because we're interested in A plus B, we're going to have A plus B being equal to tan inverse of 1, of which tan inverse of 1 is clearly 45 degrees. And remember that 45 degrees can be expressed as pi over 4. Now remember that in our logic, pi basically means 180 degrees in our knowledge of degrees. So therefore, if we are looking for 45 is like 180 divided by 4. That's why 45 degrees can be represented as pi over 4. So A plus B shall be equal to pi over 4. So now we can see that now of course we know what A is. A is tan inverse over half, and B is tan inverse over third. All of these are going to be equal to pi over 4. So let's substitute those. So now therefore we now have 1 over 5 into pi over 4. So when you multiply the 1 over 5 in, we have pi over 20, and therefore that is the proof that we are looking for. So I have an exercise for you. So you're going to express these as partial fractions, and here are the answers. And then the next part is we're going to express as partial fractions and hence evaluate the following. So these are the answers next to them. So you're going to evaluate these, and then you're going to compare the answers to what I have right there. So take time, copy the questions down, and then try them out to make sure you perfect your knowledge of this part. Otherwise, Thank you so much for watching. Thank you so much for watching this video. I hope the video really helped you. If you did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.